Hello, everyone. My name is Zhiqiang Que from Imperial College, London, working in the custom computing group. You can also call me Walking. Today, I'm going to talk about our recent research about accelerating graph neural networks for jet tagging using FPGAs. Before my talk, I would like to thank all our co-authors for their time and effort. This talk is based on our FPL 2022 paper, and we have just finished an ICAF paper earlier this month to put all of our ideas together. You can find it here. Jet tagging is an important but challenging problem at CERN LHC. Our work is focusing on accelerating a jet tagging algorithm, which is named GNNs from this paper. So basically, I'm a hardware guy, so I'm trying to accelerate this algorithm using FPGAs. GNNs is a jet tagging algorithm based on graph neural networks, and it achieves state-of-the-art accuracy. The GNN can be represented as a graph with the input of nodes and the edges. The nodes, the I matrix, corresponding to the input features of the physics particles, and the edges, the R matrix, are about the relationships between these particles. An overview of the GNN algorithm is shown in this picture. It mainly includes three matrix multiplications: the MM1, the MM2, and the MM3. And it also includes three deep neural networks: the FR, the FO, and the FIO. So the big challenge is how we can run this GNN-based GNN algorithm in low latency. For example, can we run it in 1 microsecond, below 1 microsecond for the L1 trigger? The GNN requires very large amounts of computation and has irregular memory access, leading to very large inference latency. To address these challenges, we developed a few optimizations. First, we proposed a custom strength reduction. It explores the sparsity patterns and then under the binary features of the adjacency matrix. Second, we proposed the out-product-based matrix multiplication approach, and it can be enhanced with the using the custom strength reduction. Third, we introduced the Sublayer Fusion, and the algorithm hardware coded them to further reduce the design latency. And at last, a scalable and low latency GNN template is created using Xilinx high-level synthesis language, the Vivado HLS. And our final design can achieve a latency below 1 microsecond for both 30 particles and 50 particles models. I will talk in details in the following slides. If you have any question, just interrupt me. This is a diagram of the data flow of the GNN. And let's focus on the matrix multiplication, especially the MM1 and MM2, get to the B1 and the B2 matrix. The B1 and the B2 are the multiplications between the input feature matrix and the adjacency matrix. First, let's look at the adjacency matrix in the GNN. To show the idea, here's an example of 4 particles as the input. Please note that in a real design, we'll have more particles, and our results in this talk is mainly about the 30 particle and the 50 particles. The relationship between these particles are defined in two matrices. One is the receiving matrix, the RR, and the other is the sending matrix, the RS. Under the input particle feature, the R matrix are defined as P times MO matrix. Then how we can do the matrix multiplication efficiently? From our study, most of the computational operations in this matrix multiplication are unnecessary if we exploit the patterns in the RR and RS matrix. First, the multiplications are unnecessary because the RR and RS matrix only have binary values. Second, the accumulation, the addition operations can be also avoided because each column of the RR and the RS is one hot. Thus, only load and store operations are required to finish the MM1 and MM2. Actually, one of the big issues for graph neural network is that because of the sparsities in the adjacency matrix, the memory access is very irregular. However, in the GNNs, the memory access is also unnecessary because these values can be fused into the computational loop index because of the fixed pattern in them. Like the RR will have these fixed patterns. The detailed implementation is shown in this studio code. You can find that there are no multiplications and additions when computation MM1 and MM2. Only load and store operations are needed to finish this matrix multiplication. Because the GNN is a fully connected graph, so that we have the hardware-friendly patterns here. Actually, for all the fully connected GNNs based on the interaction network architecture, the adjacency matrix are always in, sorry. They are always in a fixed pattern. So the hardware engineer can take advantage of these features and try the strength reduction, even partially. And actually, these patterns can also be designed by user to run the hardware efficiently. And then let's focus on another matrix multiplication, the MM3, because the matrix E, sorry, between the matrix E and the transpose of the receiving matrix, the E and the transpose of the receiving matrix. In the GNN, the matrix E is produced column by column. So with a traditional row-based matrix multiplication, it will have lots of irregular memory access. So to solve this issue, an old product-based matrix multiplication is proposed, which will get the matrix E column by column. And this out product-based matrix can be further enhanced by the strength reduction because the receiving matrix is binary and it has a fixed pattern. Actually, each row of the transpose of the receiving matrix is one hot, like this. So only one element is valid and will involve in the real computational computation, which can largely reduce the amounts of the computation and also reduce the output memory footprint. The strict pattern in the transpose of the receiving matrix also enable that the generation of the results is also column by column. So this is the second column of the result matrix. And here's the pseudocode. It also has no multiplication operations and only have a few addition operations. In addition, this work splits the whole GNN into several sublayers and adopts a layer-wise hardware architecture to map all the sublayers on the chip to achieve low latency. And we run these sublayers in a coarse-graded pipelining. And we also try to enroll all the fully connected layers. Here's some results of the strength reduction. The reduction of the operation and the iteration numbers are significant based on the proposed strength reduction. For example, we can remove all the multiplications. And also the latency is reduced from several milliseconds to a few microseconds with around 200 times speed up. Then with this strength reduction and the basic pipelining, we have our baseline designs, the J1 and the U1. After we get the baseline design, we are trying to reduce the latency of them. The first idea is to use more hardware resources to increase the design parallelism. Since we have several hardware units in our design, a proper partition strategy is needed. Under this design, we adopt the initial interval balancing, which proposed in this paper. For a model with multiple units in a data flow design, the system initial interval is decided by the largest one in the coarse-graded pipeline. So the idea here is that is it possible to reallocate some hardware resources from some units to the bottlenecked one to improve the overall initial interval? Actually, because some units may have a very low initial interval, which actually is unnecessary. Please see this paper for details. In this design, the bottleneck after the strength reduction is at this group. It needs to run the FR NO times NO minus 1 times. So thus, the basic idea here, the first is we allocated the unused hardware resources on the FPGA besides the baseline, the unused hardware resources to the bottleneck unit. We deploy multi-copy of the FR hardware unit to increase the parallelism. And then we apply the initial interval balancing technique to do the rebalancing to get the proper parallelism parameters based on this hardware architecture. Here are the design specs exploration for I balancing. Each blue dot is an exploit design, while the red dots are Pareto designs, following the Pareto front. This sweet spot showing the exploit design candidates which have a good trade-off between the initial intervals and the total DSPs on the U250 FPGA. So the basic idea is with more hardware resources and a proper partition strategy, we can further reduce the latency by increase the design parallelism. Then we can get 7 times lower latency for GNN 30p model, and 3 times lower latency for the GNN 50 particle model. But we are still not satisfied with the latency because we want to deploy the design in the L1 trigger system. So the target is where the target is actually less than 1 microsecond. So we have some extensions here as shown in our archive papers. After the stress reduction, some of the sublayers actually in the GNNs are very simple, like the MM1 and the MM2, and they are only load and store operations. So we can fuse these units with the next one. Usually there are ping-pong buffers on the boundary in the data flow model, in the data flow pipeline, using like the Vivado HLS. If we remove the boundary, then we can reduce the latency. So we propose to fuse the sublayers as much as possible. But some issue may appear. For the GNN designs, generally we have two parts. The first part is about the unit based on the age, which has a loop boundary of this number. While the second part is the unit on the graph nodes. So they will have a different loop bound. So actually, after the fusion, we result in such code structure within the HLS code. So this code body A is merely about the ages, and this code body B is merely about the nodes. If the code body A is very small, and then we can run the whole loop in pipeline. However, if the code body A is quite large, with this code structure putting the pipeline in here, we have to enroll, fully enroll the loop involving the code body A, this one. So it will easily occupied lots of hardware resources which cannot fit FPGAs. So in that case, we have to move the HLS pipeline programmer from the line 2 to line 4 to only pipeline the loop of code body A, and then we will not pipeline the code body B. Actually, in the Verilog design, it was quite easy because we just need to calculate how many copies of the code body A we needed, and then we just put how many copies there. However, using the high-level synthesis, we just write the C language, and then the compiler will try to convert the C template or C language-based hard into the Verilog one. So in that case, it will easily to make the design and fit the FPGA when the code body A is very large, or it will result in a very low latency, low efficient design. In this case, we proposed to FSM-based code structure to pipeline this code structure. For more details, please read our papers. So the idea is after fusion, we will have a new hardware architecture. So then we will get another 3 times faster design. Furthermore, we think we can optimize the hardware and algorithm together. So we propose a co-design framework. in this original GNN paper, the size of the FR and FO, F5O are all the same. However, the iteration for the different parts of the generate are different, just like we mentioned just now. So in our design, we think that we should decrease the size or the complexity of the FR because it needs more iterations. And we can keep or increase the size of the FO and the 5O to maintain the model accuracy. So we do a design specs exploration and found the optimal latency design and the optimal accuracy design for both GNN 30p and 50p. And this is the trade-off. And in this table, you can see that both of the model can run in less than 1 microsecond. So this is the final result. Summary of the speed up. So with the custom MMs, with the stress reduction, we can get around 200 speed up. While with the other techniques, we can further reduce the latency from several microseconds to below 1 microsecond. So our future work, the main future work will be about the automation. So some other ongoing work is we are also working on the low latency transformer designs. Sorry. So here's the summary. We proposed many optimizations and managed to reduce the GNN from several milliseconds to less than 1 microsecond. So that's all for my talk.
Yeah, thank you very much, Walkie. That was a very impressive set of optimizations that you adopted there. So I think we can open things up for questions now.
Yes, thank you.
I don't know if that's going to work, so if you've got a question, just use my laptop. To the question from Attila here in the room.
Thanks a lot for the presentation. I have a bunch of very naive questions because I know very little about FPGA programming. But first off, I was not entirely sure how many floating point calculations are we talking about? Just an order of magnitude. In order to evaluate these networks, what's the order of magnitude of float calculations that you need to execute? Because in a couple of microseconds, yeah, even GPUs can also do a good number of float calculations.
Okay. First of all, our design is using the fixed point precision. So it's not floating point precision. From my understanding, the floating point performance of the floating point on the FPGA is often not very good. So FPGA usually prefers fixed point precisions.
Okay. Do you have an order of magnitude estimate? Do we need 1 million fixed point calculations to do this inference? Do we?
Millions. I did not calculate that. You mean the operation numbers, the number of the operations, right? For example, how many multiplications and how many additions are there?
Yeah, again, as I said, I was sort of very naively looking at the presentation that I know that what you showed that that these calculations need a lot of irregular memory access, that is definitely where FPGAs are good. That no question. I was just trying to get a sense of, okay, how many calculations we need for this.
Yeah, from the GNNs, maybe I can show you the original JEDA paper because they have the number on there.
Okay.
Give me a second. Sorry.
Well, while you look for this, let me just say that I was very pleased to that you included a GitHub link with this, because I've seen so many presentations talking about FPGA code where I would never see a single line of code. But then again, my next question will be about how I browsed the code.
Sorry. What's your question?
No, okay. So first off, I see that. Okay, so millions of.
So the flops, the original GNN paper, it will include these. Yeah.
Okay. Okay. Thanks a lot. This is sort of what I was wondering about. Then I was wondering about the HLS language that you're using. This is much more of a technical question.
Yeah.
I saw that there is a lot of C++ in the code that you pointed at.
Yeah.
Is this so? Is the compiler, the HLS compiler, able to use C++ code? I thought one had to stick to just very basic C code with this.
Yeah. So the HLS compiler can convert this C++ code into hardware. This is the first. And the second, from my understanding, only a subset of the whole C++ features can support it in the compiler. So you need to follow the guidelines of the HLS user guide to see. From my understanding, most of the C++ features are supported, except the dynamic memory allocation, which is not supported on FPGAs because FPGA prefer static ones.
Okay, but that's very cool. I definitely learned something because I had no idea that one could use templating and such things.
Okay, yeah, template is supported, yes.
Yeah, very good. Thanks.
Great, thanks for the discussion.
Yeah, thank you.
Yeah, so any other hands? Stick your hand up. Yes, there's one from Mark. So go ahead, Mark.
Hi. Yeah, really nice talk, an enormous amount of work. I guess I wanted to ask maybe this specific question on, I mean, a couple of your slides, like slide 10, for example, you talk about this concatenation process. And this is just to set the context. This is a challenge we're doing an FPGA implementation of GNNs for tracking. And as we parallelize things and generate subgraphs and sub-adjacency matrices, we have to then concatenate them to create an overall graph. And I was wondering if you could say a little more about these concat processes. Is this concatenating the adjacency matrices, building a single matrix out of submatrices? And if so, how do you do that without like looping and sorting and searching? So basically more information on the concat process you show there.
Okay, so this MM3, I think you are talking about, right?
Yeah, could you say what you're concatenating? It looks like you're concatenating the, I forget what B1 is, but aren't you
mean
ultimately you have to take submatrices and concatenate them into a single adjacency matrix, right?
Yes, right, that's right.
So I guess the question is there any challenges there? I mean, can you do this without lots of looping and searching and sorting? Because are there smart ways how are you doing this?
Okay, Yeah, because from my understanding, it is quite straightforward because after we got some columns from the B1 and we got some columns from the B2, we just put them on together. And then we entered into the another iteration.
Okay, you literally just like sort of add them together. Okay.
Yeah, add them together.
We ran into trouble where there's like nodes that can be shared amongst the two. So you almost have to recreate the adjacency matrices before concatenating. Sorry, this is super technical. I can follow up with you. I was just wondering if.
Maybe it depends on the architecture of the GNN because GNN is a fully connected graph.
Okay.
So, and also like in the tracking GNN tracking based GNN algorithm, we also use the interaction networks. In the interaction networks, when the graph is a fully connected one, it always have a fixed pattern, and then you already decide, you know, where the edges, you know, which or you know which column should be combined with another column. So there's no sort, there's no search.
Okay.
Because yeah, so
Thank
because
you.
the output of the like the B1 and the B2 actually they're in fixed order.
Yeah, once they're completely fixed and separable, yeah, then it's just a simple sum. In our case, we had shared, like a node in the graph was shared with two different edges, and therefore we had to like sort of rebuild with loops. And anyway, we haven't solved this problem yet. I'll read your paper more carefully and maybe follow up, but this is a challenge for us on the tracking.
Okay.
Okay, thanks.
Okay, thanks.
Thanks, Mark. So we still have plenty of time if people have other questions.
I'll just ask a quick one. Have you looked at the resource utilization? I mean, you did a lot with latency, but I mean, are these designs that fit comfortably in a U250?
Yes. Your paper. Let's show our paper.
Okay, it's in the paper, not the talk. Yeah.
Not talk. Yeah, because there's so many.
It's
so
okay,
many
not
things.
but I mean, normally you want to like not fill up. So if this is being run with other algorithms, okay, but if you don't want to like completely fill up the FPGA because then it can't route and all this stuff. So
yes, yeah. Actually, we there's some interesting results for you. For example, with the FPL design, we have nearly used almost all the hardware sources. Well, after the fusion, we found that we only need less resources, and even we can get the better performance. This is for the DSPs, while for the LUT large, has more. So also the large also with are reduced. It's very promising. So
this is promising. Yeah, because these are the U250 is like a current device, but you know, years from now when this will be deployed, they'll be much bigger, like Versa Lake. Okay, so this fits. I mean, because your model is quite rich, it fits in the current devices. That's great.
Yeah.
Okay, that's all. Thank you.
Okay, great. Thank you.
Thanks for the question, Mark. Thanks for the clarifications, Wilkie. So any other questions that you would like to ask? Maybe I'll just ask one. Again, it's a super naive question because I'm not at all an expert in this. So you showed results for 30 particles and 50 particles. And I thought it was quite remarkable how at the end of the optimization process, your 50 particle network was almost as fast and didn't seem to be using many more resources than the 30 particle network. So just from the physics point of view, what is the target here? How big a network do you need to be able to put into L1 to be able to use this usefully?
Sorry, I did not catch that.
So it's just that, you showed an example for 30 particles and an example for 50 particles.
Yes.
And you must have thought about what would a real deployment in the trigger actually be. So is it the case of the more the better, and the 50 particle model would give you better results than the 30 particle model? Could you even go more than 50 and it would give you, this is just what I'm trying to get a handle on. What is the model that you actually want to be able to deploy at the end of the day?
Okay, so this is actually just a proof of concept. So
okay.
The real deployment will depends on the actual requirement. So in this design, we only show that with like 50 particles, you can run in less than 1 microsecond. It's possible. We did not try like the 100 and 100 or 150 particles, but we think that may need more hardware sources.
Yeah.
But if you try the particles less than 50 particles, and then we are confident that that model can be deployed on the hardware. So.
Okay, very good. So at least it's like a definite, like upper bound on where you can go there.
Yeah.
Excellent.
And also we have the 30 particle data set and the 50 particle data set. The next one is 100 particle data set. We haven't tried that.
Right.
But if we like have a 75 or 70 particle data set, then I think I will have a try. But 100 is just double of the 50 particles. I did not try that.
Okay, so you've still got some challenges to face.
Yeah, for more particles, actually, I have, actually in the HLS for ML workshop, I also be asked one question about the scalable, or if we want have more particles, what we will have. So basically, actually, for the final hardware architecture, we put together all these into just one loop.
Right.
Which means that it will look like this. So if the code body A is quite simple, in the code body A, for example, the FR and this one, and also this one, it's very simple that we can deploy many copies on the hardware, and then we can make this loop fully pipeline.
Right.
So it will only depend on the number of the particles. So the latency model will look like this. So if you have 100 particles, and then with the I is 1, it will only have 15 more, around 50 more cycles than the 50 particles data set.
Yeah, so you have a good idea of the scaling if you can apply that.
Yeah. So it depends on the size of the code body A.
Yeah. And
also it depends on the accuracy. If we can put a very simple one on hardware, but the accuracy is very poor, then it will be not good. So that's what we propose, that we should co-optimize the algorithm and the hardware together. Yeah.
Great, thanks.
Maybe I could make a comment, Graham.
Yeah, go ahead,
Alex. I should know the answer to your question, but I've forgotten it. That's my admission.
Yeah.
I think you would run this after you've removed pilot particles, and so there's a dependence on how well you do that. My recollection is that once you've removed pilot particles, you're left with a manageable number, certainly a number that you can jet find in a current FPGA, and So this might be a little bit of a stretch. As you've said, it's now well benchmarked and we can look into it, but it's not a million miles away, I think is the answer. I wish I could remember the number, but I can't.
Okay, no problem. Thanks. Yeah. Okay, so any last questions? I'm not seeing any. Okay, so in that case, I think we can finish here. So thanks very much to Woki for the talk and for the discussion as well. It was very interesting. And we should see you in a month for the next edition of the Compute Accelerator Forum.